The homework number 3 is due on Monday, and that's the one where you need to do the StormCAD analysis of the, it's like a neighborhood that's going to be put in. So you're trying to size the appropriate pipes there. And then there's also stormwater detention, so a pond sizing aspect to that assignment as well. We've already looked over one Excel example where we were doing pond sizing, and we'll continue that today by adding hydrographs, and then look at a second example where we're sizing a pond in traditional units just to get a little bit more practice. And then I'm going to tell you about 2 different empirical methods for determining the required storage volume. These are relatively quick, somewhat less accurate than setting up the spreadsheet, but they're good to know about. Any announcement questions before we begin? Okay, just as one side announcement, if you are trying to figure out what you're going to do this summer, DOH has the co-op program, and it's provided a lot of good experience to students over the years. Their deadline is on February the 11th by 4 p.m., so that's, I think, 2 weeks away. If you're interested to apply, the application is on the DOH website, and their pay $13.50 an hour is what they pay people their first summer in the program, and then it goes up from there. All right, so let's pick up where we left off last time. This is the example that we had worked, just to refresh your memory. This example, where we had a known inflow hydrograph. We had a pond that's 65 meters wide, 65 meters long, a 300 millimeter diameter pipe with a known discharge coefficient of 0.59. And we basically wanted to find out if the pond has these dimensions, 65 by 65 with this pipe, then what would the peak outflow be? And then how long would it take to drain it to 10% of the peak? So this is where we left things. We had, of course, just used the template file, and with the length and width calculated the cross-sectional area of the pond, assuming vertical side slopes. We had the characteristics of the pipe, like its discharge coefficient and diameter, and from that calculated the pipe area. And so this given inflow hydrograph allowed us to calculate how much volume flows in during that 1 hour time period. So we multiplied by 3,600 to get the volume in cubic meters. During the first hourly increment, the accumulated volume was just how much came in during the first hour. But in subsequent hours, and this is really important, it's hard to overestimate how important this is. In subsequent hours, the way that you find out the amount of water in the pond is by the previous pond volume, meaning last hour, plus how much new flow came in this hour, and the outflow during the previous hour. So we're numerically balancing the inflow, the outflow, and how much there was in the previous hour. And what we saw by doing that is that the accumulated volume of water in the pond went up, and then when the storm stopped, it drained slowly because the pipe is letting water out of the pond at a lower rate than the water flows into the pond. So some of the intermediate steps that we had to follow through in order to do that was calculate the depth of water in the pond. It's simply a function of the area of the pond and the volume of water that's there. So we found out what was the water depth in the pond, what was the distance from the center line of the outflow pipe up to the water surface, and that's h, that is used in the orifice equation, where velocity is the square root of 2gh. So when we calculate the pond outflow, that's the area of the pipe, the discharge coefficient, and square root of 2gh. And then finally, the volume out during that increment is simply the outflow rate multiplied by 3,600. Okay, so that's a refresher. And we had found out what was going to be the maximum outflow. If you see that the peak inflow from the pond is 0.81, so that's a lot of water. If you think about 0.8 of a cubic meter every second, that's a lot of water. The maximum outflow rate for this pond was 0.231 cubic meters per second. So we're knocking it down by about to 1/3 of its peak flow. So it's doing its job. And just to illustrate and kind of highlight the difference between the inflow and the outflow, let's make a graph of the inflow versus time and the outflow versus time and put it on the same figure. So here on insert, and we're going to do a scatter plot. So that's this one, a scatter, and let's not bother adding the dots. Let's just have it be a curved plot where it's smoothed in between the data points. So scatter with smooth lines. I'll just kind of move that off to the side. So it's going to be flow rates. We want to have the inflow rate and the outflow rate over time. So here at the top, select data. And our first series, we're going to add a series that we'll call inflow. And then we will have the inflow x values. Horizontal axis is time. I'll just do this one through 19 hours since it seems like, when does our outflow stop? Maybe it's through the 18th hour. Okay, so time, and then the y values is the inflow rate. Also do that down through the same hour 18. Okay, and here you can see it's got this nice smooth curve. Of course, it dips below 0 just because it's trying to smooth the data points rather than that jagged end. It dips below 0, but we'll change it so we only display to 0 for the vertical axis. All right, so that's our first series, and let's add another series. So add another series, and this one we're going to call outflow. It will have the same horizontal axis of time 0 through hour 18. And then the y-axis, we're going to be the outflow from hours 0 to 18. All right, so this is a pretty nice illustration of what the pond is doing, and it matches up with some of these theoretical figures we've seen before of what a pond does. There's the inflow peak that's higher and sooner than the outflow peak. And so that's the whole purpose of the pond, is to delay the water and to reduce the peak flow rate. And from this figure, it's clear that the pond is achieving that. The time to peak is further to the right. The magnitude of the peak isn't as high. I suppose we probably better put in some axis titles. Let's see if we can format that. So here with this plus button, chart elements, I want to add axis titles. And then for the horizontal, we can say it is time in hours. And for the vertical, it would be flow in cubic meters per second. And then we probably, it's, I think, obvious which is which. Let me right-click on the vertical axis and format it so that it just starts at 0 as the bounds rather than that negative. Okay. Let's add a legend. Okay, so then it's more obvious which is the inflow and which is the outflow. We have a nice hydrograph. It's kind of showing us what the pond is doing. Okay. So any conceptual questions on what the spreadsheet is calculating or how a certain column is determined? Anything I can clarify before we move on? Okay, well, let me hand out this to you. We're going to consider a development where they're putting in some office buildings. So we're putting in some office buildings, and there's two rules that govern the flow that's going to come out, the stormwater flow. One set of rules says that your outflow can be 0.1 CFS of discharge for every acre that's developed. And then a different ordinance. So that first ordinance, criteria A, is a statewide ordinance. And criteria B, which is a city ordinance, says that you have to completely hold on to the first inch of precipitation with no outflow. We need one more. Oh, you've got one? Yeah. Oh, okay. So let's use the same template file for this one. Open up a fresh copy of the template that's posted on Blackboard, the blank one. We're going to have to adapt it though. Here's what that blank template looks like. You could just, if you like, paste it into a secondary tab on the one that you've already created. But we need the empty one. We're going to have to make some changes because this whole example is in traditional units. So you'll notice all the labels here was like meters and so on. So let's change it from meters of pond widths to feet. Just everywhere you see meters, change it to feet in the blank template. Including these titles here. For the inflow, instead of CMS, it's going to be CFS, cubic feet per second. Volume in is cubic feet. Okay. The problem statement gives us an inflow hydrograph that we're going to type in. Now let's see here. It says here that the maximum allowed pond depth is 6 feet. It hasn't told us the dimensions of the pond. That's part of what we're designing, is how big does it need to be. We're also designing how big should the pipe be. Those are the two factors that we are going to size. The size of the pond and the size of the pipe. Okay, so where it had 65 by 65, let's just leave that for now and see what a 65-foot by 65-foot pond does. But let's put in the inflow hydrograph. So 0 CFS, 1.8, and so on. Type in your inflow hydrograph. And then all the other hours, it's just going to be 0. You see how it only goes through 23 hours right now? We're not exactly sure when we start this process how long it's going to take for the pond to drain. So just to give ourselves some wiggle room, let's extend that down through 48 hours. We'll look at how the pond behaves over a 2-day time frame. So just continue dragging those numbers down until it gets down through 48. And then, of course, extend the 0 flow rate all the way to 48 hours. Okay. So then how do we calculate the volume in during the time increment? Anybody recall how this column is calculated? Multiply the inflow rate by 3,600 seconds per hour, and then that'll give you the inflow volume. So flow rate times 3,600, because that's how many seconds there are in an hour. Okay. And at time 0, there's no water in the pond. The pond depth is 0. The H is 0. The outflow is 0, the volume out is 0. So everything's 0 at time 0. Like before the storm begins, there's nothing in the pond. Okay, but at the end of the first hour, the accumulated volume is just how much flowed in during that hour. And we're assuming that during that increment, there was no outflow. Of course, there was a little bit of outflow, but this is a numerical integration where the size of our steps is 1 hour. This may be familiar to you thinking back to calculus and how you did integration of area under the curve. The more fine your time resolution is, the better your result. And we're just going to do 1 hour steps here. But the accumulated volume in the first hour is just how much flowed in. So what will be the depth of the pond if it's 65 by 65? Okay, so it is the volume of water in the pond divided by the pond's area. Not the pipe area, by the way. The pond area. And anchor that reference because we're going to be dragging this down. We always want to have it look at the pond area field. All right. And the depth to the centroid. By the way, let's change this from a 1 foot diameter, 0.3 foot diameter. Let's just try 1 foot diameter. Because before, remember, it was in meters. So let's change the pipe to say it's a 12-inch pipe, 1 foot in diameter. So H, just to refresh your memory how that works, we have the bottom of our pond, and then there's a pipe where the water is flowing through the pipe, and H is the distance from the centroid of the pipe up to the water surface, where this is the depth. So the depth is bigger than H. We have to subtract out half the diameter of the pipe to get H. So H is the pond depth minus the pipe diameter, anchor that reference, times 0.5. So if the depth of the water is 1.5 and the pipe diameter is 1, half the pipe diameter is 0.5, so the water depth you can see 1.034. Okay? What's the formula we use for the outflow from this pond? What's the equation that governs flow out through this pond?
Q equals CB times area plus square root of 2pH.
That's right. That's the formula. What's the name of that formula? Orifice equation. Good. Yep. We're just pretending like this pond is an orifice, has an orifice in the side, which it does. That pipe is effectively an orifice that water is flowing out. Okay. So outflow is the area of the pipe, anchor the reference, times the discharge coefficient, anchor the reference, times the square root, SQRT, of 2 times G, 32.2, times H. So I'm typing in F9 to get H. All right? So that's our outflow. And then the volume out would be the outflow rate times 3,600. Something's wrong. There's got to be a mistake here. Because we can't have more flowing out than there is in the pond itself. I might have just, you know how I said let's start with a 1 foot diameter? That may be an indication that 1 foot is too big. If you have more flowing out than you had flowing in during the time increment. Let me change this. Instead of using a foot diameter, let's say, how do things work if it's 0.5 foot in diameter? So if that's the case, then I think we'll get some meaningful numerical calculations now, because at least as far as the beginning of the storm, we don't want a higher flow rate out than flowing in. That would be the opposite of what we're trying to achieve with this pond. We want the pond to release less water out than is coming in. Remember, the peak flow rate from the pond is supposed to be lower. So we've already made our first design adjustment, and that is a 1 foot diameter pipe would be too big. So we're starting with half a foot diameter. Okay. So now the only other manual thing that we have to calculate is this accumulated volume in the second hour. The rest of it we'll just be able to drag in. But remember, in the second hour, the accumulated volume is the previous hour's accumulated volume plus the volume in during this time increment minus the flow out in the previous hour. Okay? And now we can drag these other calculations down to the next row. Any questions so far at this point? So then let's just do it through the whole rest of the spreadsheet. I'm going to double click here, and what that'll do is it will apply the calculations down as far as there's still numbers to the left of this column. All right. So well, it looks fine at first glance. The peak flow rate in is 7.9. What's our peak flow rate out? 3.8. So it is reducing the peak. It's cut the peak in half. But what's our limit? This says that the limit is you're not supposed to have more than 0.1 CFS per acre. How many acres are we developing in this example? 5 acres. So our maximum outflow, the Q out max that this problem specifies, is going to be 0.5 CFS. 0.5 CFS is what the rules say we can discharge from our pond. So how much is going out of our pond? Way more than that. What was the other rule besides the discharge limit?
Maximum pond depth.
Maximum pond depth is 6 feet. And the reason for that is, like, you don't want some big gigantic dam right next to an office park. Dams are dangerous. When you've got a big tall column of water, if it fails, then a huge flow could inundate what's downstream of it. So, partly for safety reasons, you want to limit the depth of water in a pond. It's also a drowning risk. There are some issues like the bottom of the pond can get anoxic conditions if it's so deep that wind won't stir it up. So there's a variety of reasons why you'd maybe have that maximum depth limit of 6 feet. How deep is our pond getting? Oh, really deep, 17 feet. Okay, so the water's flowing out too quickly and the water depth is getting too high. Go ahead.
I don't think it makes a major difference, but I think the pipe CD for this problem is 0.6.
You are absolutely correct. And you're also right that it's not going to make a big difference, but let's put in the right data. I'm glad you caught that. Okay. So 0.6 is the discharge coefficient. Our pond depth is still too tall, and our flow rate is still too high. Design is an iterative process. Iterative means you have to make changes, check to see what happens. Make changes, check to see what happens. So how are we going to fix this design? What do we have to do to make it so that it's not so deep and there's not so much flow going out through the pipe? Make it bigger. So we're going to make it longer and wider. It was 65 by 65 before. Let's just see if 100 by 100 takes things in the right direction. The right direction being the pond isn't so deep and the flow rate isn't so large. So if you type in 100 and it's 100 by 100, yeah, that did take things in the right direction. Our pond depth is down from 17 to only 10. Our peak flow rate used to be 3.8. Now it's down to 2.8. Well, what about 150 by 150? Okay. Yeah, things are looking better. Instead of manually changing it over and over and over again, what tool do we sometimes use to automate that process?
Goal seek.
Goal seek, right.
I would do the outflow because the height, the depth is already good.
All right. So it looks like our pond depth, if we're at 150 by 150, we're good as far as the 6 foot limit. So we're within that design constraint, but we're still letting out too much water. Remember, there's two things that we're changing. We're not just changing the size, we're also changing the pipe diameter. And so let's try, instead of changing the pond width, because right now the width is mostly going to affect the depth. The thing that has the biggest control over the outflow, although the depth is a factor, the other factor is the pipe area. So we need to make that pipe smaller so it doesn't release so much water. Let's take a look at 0.25. Now this is going to change both the depth and the outflow. Our depth is now back over 6 feet, but the outflows are way closer to where they need to be. All right, so then let's make the pond a little bit bigger, like maybe 160. All right, our depth is now back below 6 feet, so that's a plus. Our outflow is still a bit high. Our limit is 0.5. We need to stay below 0.5 and we're above it. I'm going to add a column here, so just so that I don't have to keep scanning down, I'm going to have it tell me what's the maximum depth and the maximum outflow. So I'm going to do equals, not sum, max. So if you do this, it's going to return what is the maximum value inside of that range. And so it's looking for me and telling me that the maximum pond depth it sees is 5.8. And then I'll do that same max function over here for the outflow. And now the goal seek maybe is a little bit easier. Because if I was doing goal seek and I was down in the body of the spreadsheet, the location of the highest value could be a row lower or a row higher depending on the inflow versus the outflow. It's not always going to be in the same hour that you have the maxima. So now let me do the goal seek. So I've got this, it's just reporting what's the maximum within the range. So data, what if analysis, goal seek. I want to set this outflow to 0.5 by changing the pipe diameter. Okay. All right. Wow, that looks pretty good. So now we're at exactly 0.5 CFS for our maximum discharge. Our maximum pond depth is 5.9. And this is all achieved with a pipe diameter of 0.234. So what that all means is probably what we do is put in a 3-inch pipe, because 3 inches is 1/4 foot. And then we'd put just maybe a small restrictor plate on the front of it. Like the pipe itself would be 3 inches, and then it would have welded onto the front of that pipe just a little bit of a restrictor to reduce the effective flow area. Okay, any questions about this design illustration? That was our first constraint that we've solved, 0.1 CFS per acre. Now retain the first inch of precipitation. What we're saying is we have a 5-acre site with a C value of 0.7. So we want to retain in the pond our Q, well, let's actually not call it Q, it's the volume. The volume of water retained is going to be 0.7, which is the discharge coefficient, 1 inch, which is 1/12 of a foot, and then the area of 5 acres, 5 acres times 43,560 square feet per acre. So if you do those calculations, it's 12,705 cubic feet that should be in the pond before there's a drop of water going out of the pond. And just to skip ahead a bit, the way that you achieve that, the way that you achieve some storage without any outflow, is you just raise the pipe off the bottom of the pond. So here's the pond, and then the pipe actually is coming in like this. And so now H is, here's H. There's some storage volume at the bottom of the pond. Just for sake of time, we won't go through the process of doing the calculations there, but what you do is you would make an adjustment to your spreadsheet to delink H from the pond depth. You'd say H is maybe try an inch or 2 inches or 3 inches higher than the bottom of the tank, and so then the depth would be this distance minus half the pipe diameter, and then that's how you get H. H would be depth minus the offset minus half the pipe diameter. And so I did that process and found that you need to raise the outflow pipe 0.62 feet above the bottom in order to make it so that the pond is storing a certain volume of water before there's any discharge. It's actually going to store more than this minimum required amount because we're going in like 1 hour steps. So hopefully conceptually that makes sense. The specific number crunching on this criteria B maybe is something we could think about another day. But are there any pond related questions before we just move on to these empirical methods? No? All right. So this was sophisticated because we had, where's my hydrograph that we made? Did I delete that? Yeah, we made this hydrograph. We knew step by step, hour by hour, what's the flow rate in, and we calculated the flow rate out as a function of how deep the water is in the pond. These other empirical methods, like the AASHTO approach, for example, says, what if we only know the peak flow out of the pond? And so Q sub A is the outflow hydrograph, and you can see it's assuming a triangular distribution. It's assuming that the water goes up in a linear manner till it achieves some peak, and then it starts draining and reducing in a linear way. In reality, there isn't going to be a linear inflow and a linear outflow. The hydrographs have a curved shape, but sometimes you don't have all that high resolution, and so you're just calculating what is the volume of storage that's required based on the inflow rate that is going to be known to be the peak. And that could be that maybe historically there was some measurement of the flow coming off of a watershed, or remember that the rational method gives you the peak flow rate. So when we say Q equals CIA, that doesn't give us a hydrograph of outflow versus time. Q equals CIA is just, the Q here is the peak flow that's coming off of a watershed. So that would be this value. And what the AASHTO method says is you can calculate the storage volume just by calculating the area underneath the inflow hydrograph that is above the outflow hydrograph. So here's the formula for that. And we're going to, in just a moment, after I show you the other approach, compare the two and get some practice using them. So the Abt and Grigg estimate is a little bit more sophisticated than AASHTO approach because you know how a pond operates. A pond fills up, it releases water, and then it stops. The pond won't have a triangular outflow hydrograph. And the Abt and Grigg approach just says, well, let's assume that the pond is filling, it's releasing water at a constant rate, which that's not accurate. It won't do that, but it's more accurate that it would be flat as the discharge curve than go to a point like this. So just a different way of looking at it, and again, we're calculating the storage volume that's required using just kind of an area under the curve approach. So here's the formula for that. And in this example, we're going to compare the two. Let's say that we want to know the estimated pond volume that's required. So V sub S, according to both methods. Calculate V sub S. if the peak runoff flow rate is 450 liters per second, so that is talking about Q sub P, 450 liters per second. The allowable discharge is 80 liters per second, so that's the Q sub A. And then the inflow discharge duration is 90 minutes. So 90 minutes is talking about how long from the beginning of the storm until the time of the peak. And that's, this base time is double the time to the peak. And so if we're given the time to the peak, then you would multiply the base time times 0.5, or I guess that's just the time to peak. We could put T sub P in front of the V sub S. All right, so let me pause for a second, give you a chance to do these calculations. Feel free to discuss it with your classmates, and we'll look at the solution in just a moment. Okay, we need to convert the given liters per second into cubic meters per second in order to substitute them into this formula. And of course, there's 1,000 liters in a cubic meter. So here you can see that for the AASHTO approach, we're having 1/2 times the base time. So that takes us to the time to peak, essentially. If the base time, meaning the entire duration of the runoff of the storm, is 5,400 seconds, which is 90 minutes, then we'll get 999 cubic meters is the required storage volume according to the AASHTO approach. Abt and Grigg gets us in the same ballpark, similar. We need to calculate the V sub R, so that is the retained volume. Excuse me, the total runoff volume. And so the pond itself is only going to be 821 meters, because during the storm we're going to release some of the flow. It'll just pass straight through the pond and not be retained. So these are ways to estimate the volume, but what they don't tell you necessarily is how deep the water in the pond would be. We haven't, with this approach, sized the diameter of the orifice. This is just telling us the required storage volume. But I think you have a homework problem perhaps that asks you to apply these empirical equations, so now that you've seen them. All right, well that's all for today. Just as a reminder, your homework 3 is due on Monday. And so if you have StormCAD or spreadsheet related questions, I have office hours today from 1 till 2. I'd be happy to help you then, or you can just get in touch with me on Teams or by email, and I'll do my best to help you out. So have a good weekend. I'll see you on Monday.